Welcome to the next video. This exercise is based on the theorem of ratios of areas of two similar triangles. We know that the ratio of areas of two similar triangles is equal to the ratio of the square of their corresponding sides. Not only the sides, but also the ratio of the squares of their corresponding altitudes, angle bisectors, and medians. Okay, so this whole exercise is based on the theorems concerning ratios of areas of similar triangles. Okay, let's start. Let triangle ABC be similar to triangle DEF. Now, without looking at the figure, we can apply the theorem because we know now the correspondence works uh, when you have to find the ratios of corresponding sides. So if you know the names of similar triangle, you can figure out the correspondence, and if you figure out the correspondence, then you can find the corresponding sides. So the areas of triangle ABC is 64 centimeter square, and triangle DEF if is 121 centimeter square. If EF is 15.4 centimeter, find BC. Very easy. So we know that area of triangle ABC upon area of triangle DEF is equal to BC square upon EF square. So this will be 64 upon 121 is equal to BC square upon 15.4 the whole square. So BC square is equal to 64 multiplied by 15.4 multiplied by 15.4 because it's a square upon 121. Please pause the video, note this much down, do the calculation and find the answer. In the meanwhile, I will also find the answer. 64 multiplied by 15.4 multiplied by 15.4 divided by 121. Okay, so the answer comes out to be 125.44. So therefore BC will be under root of 125.44. Now take its square root. So square root of 125.44 is 11.2. So BC will be 11.2 centimeter. Let's check the answer. It was pretty straightforward, right? Only one thing I did not write, which I will write now. Here I have to mention the theorem. The ratios of areas, ratio, not ratios, ratio of areas of two similar triangles, ratio of areas of two similar triangles is equal to ratio of the squares of their corresponding sides. So some student might have this question in their mind that do we have to write the full theorem? Yes, absolutely, you have to write the full theorem. There is no shortcut like BPT for this. So still, I think you should ask your teacher whether to write full theorem or how much to write or what to write. But according to me, you have to write the full statement over here, like how I have written. Let's check the answer. Correct, 11.2. Let's go ahead. Okay, so we have a figure. Let's take it. Okay, diagonals of trapezium ABCD with AB parallel to CD, AB parallel to DC. See, AB is parallel to DC. The diagonals of this trapezium where AB is parallel to DC is they intersect at point O. If AB is 2 times CD, if AB is 2 times CD, find the ratio of the areas of triangle AOB and triangle COD. Okay, first we have to prove triangle AOB and triangle COD similar. So given to prove, all you have to write. Okay, I'm not writing that, not because that's not important. I'm not writing because I want to focus, save time and focus on the solution. So you have to do all those formalities. I'm very much clear with that. This may be the 6th part of the chapter. So by now I'm very clear about how I want things to be represented in proof geometry chapters. Okay, so in triangle AOB and triangle COD, angle AOB is equal to angle COD, vertically opposite angles. Angle OAB is equal to angle OCD, alternate interior angles, and therefore triangle AOB similar to triangle. Let's check the correspondence. A is corresponding with C, O is corresponding with O, and B is corresponding with D by AA similarity, and therefore we can say that area of triangle AOB upon area of triangle COD is equal to AB square upon CD square, right? Here you will write the full theorem which I have already discussed with you. The ratio of areas of two similar triangles is equal to the ratio of the square of their corresponding sides. Okay, now we know that AB is equal to 2 times CD, so we can write 2CD the whole square, and here CD square, 4CD square upon CD square, CD square gets cut. 4:1 is your answer. Let's check the answer. I hope you understood the method. Correct, 4:1. Let's go ahead. In given figure, ABC and DBC are two triangles on the same base. ABC, DBC. ABC, DBC. Let me. This is ABC and this is DBC. Okay. If AD intersects BC at O, prove that area of triangle ABC upon area of triangle DBC is equal to AO upon DO. Okay, that is interesting. See, they have not given us that AC is parallel to BD, or are there any similar triangles, any similarity existing between ABC and DBC? Nothing like that is given. Just that ABC and DBC are on the same base, and AD and BC intersected too. Nothing except that. Okay, we don't even know that is this perpendicular or not. Okay, think a little. You have to think a little. We can try to do one construction, because see, area is involved, but we don't have similarity or any other information regarding how to prove these two triangles similar or anything like that. So we can do a construction in both the triangles. Let's draw a perpendicular from A to BC, and let's call it AM. Also draw a perpendicular from D to BC, and let's call it DN. So we have, let's write given triangle ABC and DBC both lie on common base BC. Number one, AD intersects BC at O. Number two, to prove area of triangle ABC upon area of triangle DBC is equal to AO upon DU, and construction, draw AM perpendicular to BC, comma, DN perpendicular to BC. Proof. Let's start from here. What is area of triangle ABC now? Area of triangle ABC is half into base, that is BC, into height, which is AM. Okay, and what is area of triangle DBC now? That is half into base BC into height DN. Therefore, area of triangle ABC upon area of triangle DBC is equal to half into BC into AM upon half into BC multiplied by DN. BC gets cut, half gets cut, so we get AM upon DN. Number one. Okay, this is equation number one. We have got area of triangle ABC upon area of triangle DBC's ratio as AM upon DN. This is M. Now in triangle, see, this is, you have to write this separately. Okay, you can start with this or with this part which I'm writing right now, whichever is okay. So in triangle AOM and triangle DON, Angle AOM is equal to angle DON, vertically opposite angles. Angle AMO is equal to angle DNO, both 90 degree. Therefore, triangle AOM, triangle AOM is similar, wait, triangle AOM is similar to triangle DON by AA similarity. Okay, so we can say that therefore AM upon DN is equal to AO upon DO, CPST, corresponding parts of similar triangles. Name it equation number 2. And from 1 and 2, you can say that, see, area of triangle ABC upon area of triangle DBC is AM upon DN, and AM upon DN is equal to AO upon DO. So area of triangle ABC upon area of triangle DBC is equal to AO upon DO. AO upon DO. Okay, so this is done. So without the construction, it was difficult to prove. And also, if you think that there was similarity involved here, similarity was involved, but not directly. Okay, next question. If the areas of two similar triangles are equal, prove that they are congruent. I think we have proved this particular theorem in the theorem part. I would like to check right now. In the theorem part, I remember that very clearly that I've proved this theorem. Okay, so this is area of two similar triangles, and no, I don't know how. I feel that I have proved something like this. Yeah, this one. If the areas of two similar triangles are equal, then the triangles are congruent. We have proved this. And if you want to see the whole proof, you can go to the theorems video and check out the whole proof. It is there already. Let me see if the question which we are seeing is also the same. If the areas of two similar triangles are equal, prove that they are congruent. Yes, absolutely same. So we are not going to do it again. Although for practice, I advise all of you to remember this theorem and solve it again, because this is important. Okay, so you can pause the video here and solve this theorem and then move ahead. Okay, this one is an interesting question. Okay, let's see. D, E, and F are midpoints of sides BC, CA, and AB respectively. So D, E and F are midpoints. Let me mark the midpoints. So D is midpoint of BC, E is midpoint of AC, and F is midpoint of AB. So BD is equal to DC, as we can see in the figure. AE is equal to EC and AF is equal to FB. Prove that area of triangle DEF upon area of triangle ABC is 1 by 4. It's a very clever theorem or proof, you can say. So given, we can write. To prove, we can write. Construction, there is none, so no need to write construction. So how to prove this? See, we have to compare the areas of triangle DEF and triangle ABC. So first we have to prove them similar. Okay. For proving them similar, see what we can do. In triangle ABC, F is midpoint of AB. So therefore AF is equal to FB, and hey, why not use midpoint theorem directly? Yes. So let's use midpoint theorem directly. In triangle ABC, F and E are midpoints of sides AB and AC respectively. Therefore, FE will be parallel to BC and FE will be half of BC. You know why? By midpoint theorem. By midpoint theorem, FE will be parallel to BC and FE will be half of BC. Okay. Now, D is midpoint of BC. Therefore, BD is also half of BC. So therefore, FEDB, FEDB is a parallelogram. FEDB is a parallelogram. Okay. See, our motive was to prove triangle ABC and DEF similar to each other, and then we can use the theorem of ratios of areas of two similar triangles, and that is possible, but you need to be patient a little bit. FEDB is a parallelogram. Why is it a parallelogram? One, since one pair of opposite sides are equal and parallel. Which pair am I talking about? I am talking about I think I should mention here. Therefore, FE is parallel to BD and FE is equal to BD. FE becomes parallel to BD because FE is parallel to BC, so it has to be parallel to BD, and FE and BD both are half of BC, so FE is equal to BD, and since one pair of opposite sides are equal and parallel, FEDB is a parallelogram. Similarly, see, Similarly, we can prove that FECD is also a FECD is also a parallelogram, right? Because see, FE will be parallel to DC and FE will be equal to DC because FE and DC both are half of BC, right? So FECD is also a parallelogram. So therefore, we can say that angle FED is equal to angle FBD and angle EFD is equal to angle EFD is equal to angle ECD. EFD is equal to ECD. Why so? Because they are opposite angles of parallelogram. Opposite angles of parallelogram are equal. So which angle am I talking about, See, this angle being equal to this angle, since this is a parallelogram, correct? And I'm talking about this angle being equal to this angle, since this is also a parallelogram, FECD. So do you see two parallelograms overlapping each other, red one and the green one, right? So what I have proved is that their opposite angles are equal because they are parallelograms. Now things will become very simple. Okay, pay attention now. In triangle ABC and triangle uh, DEF, ABC and DEF, angle ABC, the red cross, is equal to angle DEF. Angle ACB is equal to the green cross, angle DFE. Why? Because we have already proved them. They are opposite angles of parallelogram. Therefore, triangle ABC must be similar to triangle DEF, right? By AA similarity. And therefore, you can say that area of similar triangles, the ratio of areas of similar triangles, right? So, area of triangle ABC upon area of triangle DEF is equal to BC square upon EF square. BC square upon EF square. Sorry. But we have already proved that FE or EF is half of BC. So we can write it as BC square upon half BC the whole square. Right? That is BC square upon BC square by 4. So that is 4 is to 1 because this 4 will go up and BC will cut, so we'll get 4 is to 1. This is what we had to prove. We had to prove that area of that small triangle, which is made by joining the midpoints of any big triangle, is 1/4 the area of the bigger triangle. Okay, so here what they are asking us to prove is the reverse of what we just proved, but it's absolutely same. Area of triangle DEF upon area of triangle ABC is 1/4, but we have proved area of triangle ABC upon area of triangle DEF as 4/1. 4 is to 1. So it is absolutely same. If you want to write the same answer, you can write it after this. after the final answer which we have derived, but the method is absolutely correct, right? Let's go ahead. Okay, this one we have already proved that the ratio of areas of two similar triangles is equal to the ratio of their corresponding medians. In the theorem section you will find this proof. See, always remember that ratio of areas of two similar triangles is equal to the ratio of their corresponding medians. I'm sorry, the ratio the yes, so what I mean to say is, if two triangles are similar, the ratio of their corresponding sides is equal to their ratio of their corresponding medians, altitudes and angle bisector. But also if two triangles are similar, the ratio of their areas is equal to the ratio of their squares of their corresponding sides, corresponding medians, corresponding altitudes and corresponding angle bisectors. This is the theorem which we were talking about, but for the sake of let's say, because I think I had asked you guys to prove that theorem for me, and I don't know how many of you did it, how many of you have still doubt in that. So just for the sake of it, I'm going to prove it again for you very fast and show it to you that how we can prove this. Let's do it. So these are two triangles ABC and PQR. So in triangle ABC and PQR, AD and PS are the medians. So BD is equal to DC and QS is equal to SR. Okay, and it is given that triangle ABC is similar to triangle PQR. Triangle ABC is similar to triangle PQR, and AD and PS are the medians. Okay, AD and PS are the medians. To prove, we have to write that area of triangle ABC upon area of triangle PQR is equal to AD square upon PS square. Okay, so let's start with the proof. Now in proof you have to first write that AB upon PQ is equal to BC upon QR. Why? CPST, corresponding parts of similar triangles. So therefore you can also say that AB upon PQ is equal to half BC upon half QR. Half BC and half QR. You know what is half BC? Half BC is BD and half QR is QS. So therefore we can say that AB upon PQ is equal to BD upon QS. Alright. Also, angle ABD is equal to angle PQS CPST. You know which angle I'm talking about? I'm talking about these two angles. They are equal in original triangle ABC and PQR because they are similar. So their corresponding angles will be equal. Okay, so we can say that therefore triangle ABD will be similar to triangle PQS. See, we have proved triangle ABD and PQS similar by SAS similarity. If you see over here, I have proved that AB upon PQ is equal to BD upon QS and angle ABD is equal to angle PQS. So triangle ABD and PQS become similar triangles, and therefore we can say that AB upon PQ is equal to AD upon PS. Why? CPST. And therefore, area of triangle ABC upon area of triangle PQR, in the place of see, we know that area of triangle ABC upon area of triangle PQR is AB square upon PQ square. Now you must write the whole theorem over here. The ratio of areas of two similar triangles is equal to the ratio of the square of their corresponding sides. The whole theorem. After that, you have to mention here, therefore, area of triangle ABC upon area of triangle PQR is equal to see, AB upon PQ is equal to AD upon PS, so you can write AD square upon PS square, AD square upon PS square, correct? So that is it, we have proved it, hence proved. You can write it, and you can give a reason also over here, since AB upon PQ is equal to AD upon PS. Okay, so this is the classic theorem, and the similar note you will find theorems where you have to prove that a ratio of area of two similar triangles is equal to the ratio of their corresponding angle bisectors as well as altitudes, which I have already discussed in the theorem part, and this one I have proved for you all as well. So now there should be no confusion. Okay, this one is interesting. Okay, hold on. Okay, what does it say? Prove that area of an equilateral triangle described on one side of a square, okay, is equal to half the area of equilateral triangle described on one of the diagonal of the square. Now, do you see over here, I'm just going to highlight two triangles. Do you see that triangle CBE is an equilateral triangle which is described on the side BC of a square ABCD, where AB is equal to BC is equal to CD is equal to AD. And do you see that triangle ACE is another equilateral triangle which is described on the diagonal of the square ABCD. Now, first, before I go to the question, I would like to ask you, do you know the relationship between the side of the square and the diagonal of the square? Or do you know the formula for diagonal of a square? Diagonal of a square is equal to root 2 times side, root 2 times the side of the square. Okay, remember this formula because we are going to use it in this question. So we have to prove that the ratio of area of the equilateral triangles described on the side and on the diagonal is equal to 1 by 2, or area of the triangle on described on the one side of a square is half the area of the equilateral triangle described on its diagonal. Okay, so let's write given over here properly. ABCD is a square. ABCD is a square triangle CBE is is an equilateral triangle on the side CB of square, and triangle ACE is also an equilateral triangle on the side AC, sorry, on the diagonal AC, I'm sorry, on the diagonal AC of square ABCD. Okay, so triangle ACE is also an equilateral triangle, triangle CBE is also an equilateral triangle, and we have to prove that area of triangle CBE upon area of triangle ACE is equal to 1 by 2. No construction, nothing is required. So directly the proof, see, triangle ACE is similar to triangle CBE. You know why they are similar? Triangle ACE and CBE are similar since they are equilateral. All equilateral triangles are similar to each other, so there is no question asked. Therefore, area of triangle CBE upon area of triangle ACE is equal to CB square upon AC square. Okay, now CB is the side of the square, so side of the square is A, so I will write it as A square, and AC is the diagonal of the square, which I already told you, which is root 2 times A, so I will write root 2A the whole square, so that is A square upon 2A square, A square cancel, 1 by 2, or 1 is to 2. So we can now say that the area of equilateral triangle on the side is half the area of equilateral triangle on the diagonal. Okay, so that is 1 is to 2. Great, easy. Okay, tick the correct answer and justify. ABC and BDE are two equilateral triangles such that D is midpoint of BC and E is midpoint of BC. No, that's not given. Okay, such that D is midpoint of BC. The ratio of triangle ABC and BDE is 2 is to 1, 1 is to 2. Just a moment. Okay, now it's fine. ABC and BDE are two equilateral triangles. If they are equilateral triangle and D is midpoint of BC, then we know that BD will be equal to DC and BD is also equal to BE, right? And we know that AB is equal to CD. So if AB is equal to BC, I'm sorry, if AB is equal to BC and BE is equal to BD, therefore DC will also, and DC is equal to BD, of course, so BE will also be equal to AE. Correct? So these two, D and E, become the midpoints. We have to find the ratio of the area of triangle ABC and BDE. Now, since they are equilateral triangles, they will be also similar. Okay, so area of triangle ABC upon area of triangle BDE will be equal to AB square. I'm not maintain the correspondence. If I'm writing ABC, then here I should write according to the correspondence EBD. So AB square upon EB square. Now AB and EB, they are both EB is half of AB, right? So I can write it as 2EB the whole square upon EB square, right? Because AB is 2 times EB. So 4EB square upon EB square, which is 4 is to 1. 4 is to 1. Okay, so ratio of areas of triangle ABC and BDE is 4 is to 1. The C is correct answer. Let's check. Yes, 4 is to 1. Okay, sides of two similar triangles are in the ratio 4 is to 9. The areas of these two triangles are in the ratio. We know that the ratio of areas of two similar triangles is equal to the ratio of the square of their corresponding sides. So if we square 4 and 9, we'll get 16 is to 81. So D is the correct answer. 16 is to 81. Yes. Okay, so that was the exercise 6.4. We have completed, we have done almost all the questions. And now we are just left with one part in the chapter. I have to make two videos that is based on Pythagoras theorem. Okay, so all the theorems involving Pythagoras, or you can say the results based on Pythagoras theorem, as well as Pythagoras theorem itself, and then the exercise 6.5. So I think two more videos and chapter triangle, which is a huge chapter, will be over. Okay, so yeah, some of the students are saying that their exams are coming and this chapter is involved. As you can see that I'm trying my best to finish the chapter before your exam, but it's a huge chapter. I don't want to just do it for the sake of finishing it. Okay, so I will take time, and uh, if I cannot finish before your exam, I'm afraid so that cannot happen. But I'm trying. Okay, so I'll see you in the next video. Bye bye.